folks, OCA here. If you have already run an auto calibration with Multi-EQ Editor app using the Odyssey microphone and are not satisfied with the results, or you like your surround sound but are wondering if it can be improved, this tutorial is the right one for you. Whether you're using a Dolby Atmos or an Oro 3D setup, you'll be able to precisely calibrate your immersive audio without having to purchase a calibration microphone or make any additional measurements. In previous Odyssey tutorials, we used special Atmos sweeps in Room EQ Wizard to obtain responses of our Atmos speakers, but it's not technically possible to produce such sweeps for the Oro 3D speaker configuration. Also, Mac users had difficulties playing the Atmos sweeps from the height channels. However, with this method, it's possible to optimize an Oro setup by hacking Odyssey's own measurements. Odyssey measurements are almost identical to REW measurements taken by UMIC microphones because a correction is applied to them within the app for the ACM1HB Odyssey microphone. And there are 8 different measurements taken at different positions in the room for each of your speakers. It's possible to upload these measurements to REW, and once they are in the Room EQ Wizard, the options are vast to create an optimal correction filter for your system. In this tutorial, I'll show you a very precise and effective method far beyond the limits of Odyssey's own algorithm. So let's begin. After completing an auto calibration with your Multi-EQ Editor app, you need to transfer the created app file to your computer. The process is pretty straightforward. Select the measurement file, click the send button on the top left corner of your tablet or phone, choose send a copy instead of send to AVR. You have multiple options here to send it to your computer. You can use your cloud drive or even use Bluetooth to directly send it to your computer. Once you have the DWI file in your computer, open your web browser, search for JSON Online Editor, and the first hit is a very good online editor. Drop your ADY file into the browser. This ADY file, in fact, is a JSON file, and this is inside your Multi-EQ Editor measurement. As you see, Oro is ticked as true. 14 detected channels. Channel 0 is front left channel, command ID FL, and the response data, there are 8 different measurement positions for the microphone. Measurement 0 is the central position, and the other 7 are following microphone positions for front left channel. Similarly, for center channel, represented by C, you have again 8 measurements, each containing 16,384 impulse data, which are the measurements Odyssey took in your system. You will see that, for example, channel 11 is a center high channel, and channel 12 is top speaker, which is the voice of God, and these are Oro specific channels, and we have their measurements, so we didn't need to measure them with UMIC in REW. This is just to show you the contents of this measurement. We don't need to see it. Now we can start to dig into this ADY file and move it to REW. Editing these JSON files, copy pasting large amounts of data in a specific format, and especially for the particular method in this video, extracting 8 measurements from each speaker in your system and saving them as REW compatible impulse files would be a lot of work with Excel and would be prone to user errors. Even Python scripts require a lot of installation to work properly and is not suitable for everyone. Most importantly, an Odyssey tutorial had to be cross-platform, especially for Mac users who could never play Atmos sweeps to measure them. So I wrote HTML code snippets which work from within your browser. They work in any platform with an internet browser and require no installation whatsoever, and they will do all the work for you related to your measurement ADY file. These are just 2 small programs named Extract them and Correct them, and the third file you see here on screen is the original Multi-EQ app measurement transferred from my phone named Oro 3D. These 3 files, along with an installation of Room EQ Wizard, are all we need to achieve great improvement over standard Odyssey calibration. I will provide a download link in the description section under the video for both code snippets. They have almost no user interface thanks to my total of 5 hours HTML coding experience, but they will do the job. As you see in my PC, they are opened by Google Chrome as it is the default browser, but they will work just as fine in Safari or Firefox or whatever browser you're using. I believe even Linux users will be able to hack Odyssey calibration now. We need to double click and run Extract them first. Here it comes. Choose file, and you simply choose your original measurement transferred from your phone. And once done, it first creates the perfect speaker version of this file. You save it. And here it wants to download multiple files. These are the measurements, LO. And as a zip file, it also saves all speaker responses in an REW compatible format. Here to open the zip file, as you can see, these are the original measurements for every 8 position. This is for center speaker, this is for center height, the God channel in Oro. And that's all. You don't have to do anything else with the JSON file. And to compare, for example, this was the original Oro 3D, and this is our created perfect speaker version. As you see, everything is the same, but when you go into the detect the channels and response data, here the original file has an impulse response,
But our file now has a perfect Dirac pulse, which means it's a perfect speaker, which means Odyssey will not apply any correction to this speaker. This is correct for every measurement of every other speaker, like so. Okay. The only other change it does is if it sees mid-range compensation true, it changes it to false. Otherwise, it leaves everything else the same. Okay. After that, we are done with this ADVFL and it's time to open Room EQ Wizard.
Our extracted zip file here, saved under the name responses. First we pick center channel. Let's go in the same row as the folder itself. From C0 till C7. Drag and drop them all to REW. C0 you have to put it at the top because this is the central measurement which has the correct speaker distance. You can see here. As you can see, these are quite close to each other measurements. C0 is in the middle and the user has taken measurements around 8 centimeters. So it's a tight measurement, which I suggest you do as well, especially if you're going to be sitting on your own most of the time, rather than rows of seats in a home cinema. But the method is the same, even if you have to take measurements far apart from each other. Now, with cross correlation, you have to align their impulses to each other. The one at the top here of the other measurements is the one that cross correlation will align everything to for all the selected measurements here in all SPS screen. So you go to controls and cross correlation align, and you can watch here everything being aligned to C0 like so. And once that is done, you can take a vector average over these measurements only after cross correlation alignment, and as you see, the response is very much in line with the average of measurements. If you didn't cross correlation align, you would see a major drop in the high frequencies because of the phase mismatch of different measurements. So this one now is your C measurement, and perfect average of all 8 measurements, which you can now erase, untick C so it stays, and right click remove selected measurements. 8 measurements will be removed. Are you sure? Yes. This is how we have the C. Now let's do the same for CH0. 1, 2, 3, 4, 5, 6, 7. Drop them all at once. Make sure CH0 is at the top of the other CH measurements. Unselect C. Copy selections to other overlay graphs. So every CH measurement is now in overlays. As you see, the central one is the green one, and cross correlation align. You see they all gathered on top of CH0, and now you can vector average. Call this CH for center height. You can now delete all the other CH measurements. I do it this way because if you import all of these at once, there are 112 measurements, and Rev can deal with it, but it will be quite a crowded Room EQ Wizard screen, so we only need these measurements once for the vector average. We will only use these for everything else. So that's an easier way. Again, drop all the measurements. FHL, front height left speaker, to the top of every other front height. Make sure CH and C are not ticked here. Okay, these are mistakes, very easy to do. And again, copy selections to other overlay graphs. So their timings are a bit different. Cross correlation align, aligned all of them, and vector average, which is your real response of your front height left speaker around the listening position. Again, remove the selected measurements. Now, after some considerable time dealing with all the measurements imported from your Odyssey calibration file, you have all the speakers or your Aura setup. Most of these speakers are impossible to be played through any computer because Aura signals, unlike Atmos, cannot be produced at the moment with any publicly available software at least. Anyway, now we have the average responses of every speaker in our system. As you can see, their timings are not aligned with each other, which we will fix, but not now. First, we have to do the correction. For the correction, we apply, when everything is selected, 1/48 smoothing. Then unselect the subwoofer and take a dB average of every other measurement. Okay. This is the average of all your speakers in the system. Leveling their SPL, then EQing, or EQing first and then leveling doesn't really matter because Odyssey has a certain buffer for filtering a response and they add up to each other, so they seem in line in terms of volume. I don't see any particular weird one except for the TS speaker, I guess, but even that in the mid-range doesn't seem like too loud. It could be lowered a little bit. We'll see. Now, from this dB average, you determine the target. Target settings, target type none, Harman curve Harmon, which I will provide in the description under the window. No room curve edit, and calculate target level from response. You can't see it because it's not in the screen. Now it is. It decided to fit the target level at 115.6 dB. Generate measurement from target shape. So this is our target, which we will correct every speaker for. We can call this in short just target, and you can get rid of dB average. If you check the info of target here, you will find its dB offset. This is the target level, 115.60. Sometimes it could be not 0 but 62. You have to enter this level for every speaker, whatever you see here. It accepts 2 digits after the decimal, although it doesn't show it on the window. Now, 115.60, 1 over 48 smoothing. So we go to the first speaker, go to EQ, enter here 115.6. Press the tab key, and here we are. If you want, you can fit the data. Now, filter tasks from 20 Hz to 200 Hz, 5, so maximum boost 5, overall maximum boost 5, flatness target 1, arrow narrow filters ticked, where I max Q over 200 Hz, which is irrelevant here, still ticked, okay? Then match response to target. And let Rev do its magic. As you see, it corrected up to 200 Hz almost perfectly to the curve. Now, generate measurement from filters, which generates this on the screen. These are the filters it's using. As you see, it says 0 dB, some boosting filters, some cutting filters, up to 200 Hz. And then generate measurement from predicted, which is what happens to the response after these filters are applied. So we automatically have it without having to calculate. It would be the same thing if I trace arithmetic multiplied C with filter C. It would be exactly this EQC. As you see, after the filter, our response is right over the target for the center speaker. Do this for every one of them. CH, EQ, 115.6. Match response to target, these settings don't change, and generate measurement from filters, generate measurement from predicted. Go to FHL, EQ, 115.6, match response to target, warning, ignore, generate measurement from filters, and generate measurement from predicted. You do this for every other speaker, up to the subwoofer, and you end up with all these filters. Now for the subwoofer, you have to unselect everything, target, and your subwoofer response. Actually, it is right on in this particular video. It is because this guy is equalizing his 4 subwoofers with mini DSP. The level is right on, so you don't have to do anything. Still, you have to go to EQ, 115.6. From 20 to 200, match response to target, and some more equalization on the subwoofer as well. Generate measurement from filters, generate measurement from predicted. Now, why do we have all these EQ after the first filterization responses? Let's start with EQC. Here is the target. Okay, and the data, it's something like that at the moment. So we go to EQC. Again, EQ window. Target level will not change, so you don't have to re-enter it, but just here you have to make from 200 to 500 Hz now, and 0, 0, no boost. Everything else the same, and match response to target. Click OK. And as you see now, from 200 to 500 Hz, it only cuts the peaks. Again, generate measurement from filters and generate measurement from predicted. This is a scientific method and sounds the best so far among other methods. The logic is below the room transient frequency, Schroeder's frequency, 200 Hz. It corrects for almost everything, even the dips, and up to 500 Hz there are still room reflections in the sound. It doesn't intervene in the dips, only cuts the peaks, creates the filters, as you see here, filters EQC, and the response after this filtering, which is this one. Okay, and you do this for every other EQCH. Target is same. This is not gonna change, so all you have to do is click match response to target, and once Rev does its job, generate measurement from filters and generate measurement from predicted. EQFHL, again match response to target, filters, predicted. EQFHR, match response to target, generate measurement from filters, generate measurement from predicted. And we complete up to the subwoofer. Again, for subwoofer we don't have to do it because 200 Hz is already the limit of the frequencies a subwoofer can cover or should cover. Now, the last stage of the filter, again, why we created this EQ filters, EQC and EQC. EQC now, this one here, not this one, but like this is the target. This is after the first filter, and this is after the second filter, this one. Okay, this one is the one we're gonna be dealing with. Number 43, this one, IR windows. Let's go to taking a bit of time, this thing. JSON editor online and Aura 3D. Now, from channel report of FL, or where were we? We were doing C, center speaker. Okay, so this one. Center speaker, C, channel report. The distance, according to Odyssey, was 174. At this stage, we can think of this as correct. So 174, and depending on your amplifier, the newer models correctly takes the speed of sound as 343 meters per second. But if you have any model before this year or last, maybe, I don't know, and it's not so important as long as you use the same formula for each and every one of them. In my case, it is 300, so 1.74 meters over 300, this much seconds, and this is 5.8 milliseconds. Okay, so this speaker is 5.8 milliseconds away from the LP. We shorten the right window size to 5.8, which automatically cancels the effect of every reflection in the room, because no reflection can arrive earlier than the direct sound, which is the distance to your ear and the tweeter. After this windowing, as you can see, the shape of the response changed very much, and you can no longer see below a certain 175 Hz frequency. This is due to the FFT of the response when you have this tight windowing, but we are not interested with anything below 500 because we already equalized it up to 500 Hz. So now we have EQC. Before, let's close the waterfall graph. At 5.8 milliseconds after it's produced, and the volume of the signals have lowered and the effect of all the reflections have gone. We still don't want to do very sharp filters at this over 500 Hertz range. Okay, it's gonna throttle the sound, it's gonna cause boxiness, and what you will hear really is the psychoacoustic smoothed version of this. Okay, so this is what you need to correct. Level is still there, 115.6. Now this time it's from 500 Hz to 20,000 Hz. Again, no boost, okay? Because this dip here, for example, is because of a crossover probably. And if you try to boost it, you will just ruin the sound. Match response to target. Okay. And as you see, it used only 5 filters with low Qs, and it corrected up to 13,000 Hz, which is quite rare. But this is a center speaker. It's not at ear level, so these are normal. Now generate measurements from filters. This time we don't need to generate measurement from predicted because we are no longer gonna correct this response for anything else. We only need the last filters. Similarly, you go to CH channel now and check from the JSON file CH. I wish I can find CH, maybe here, yes. Channel report 2.13 meters. So 2.13 over 300 times 1000 times, of course, 7.1 milliseconds. If your amplifier uses 343 as speed of sound, and Odyssey's distance will be calculated accordingly. You can easily understand that by really measuring your speaker distance and what Odyssey came up with. If there's a huge difference, then Odyssey is using 300. If it is almost similar within 10 centimeters, then it's using correctly 343. Some new amplifier models are using the correct speed of sound, so I can't really advise at this point which one to use. 6 months ago, you should always use 300, but I'm not sure now. As I said, just measure your real speaker distance and compare it to what Odyssey calculated, and then you will easily see. The 7.1 millisecond distance of your speaker never changes. It's just according to speed of sound, the distance traveled by sound at this much time will shorten or get longer. So this time you apply a window of 7.1 milliseconds to this CH, which was here. Okay, look, from 333. Let's remove everything else and show you the effect of it. And this is the target here. Okay, when I changed it down to 7.1 milliseconds, look what's happening in the response. Then when you apply a psychoacoustic smoothing, this will apply to also the target, which I don't like, so do it here, psychoacoustic smoothing. Okay. And now go and match response to target. As you see, it's perfectly equalizing it without causing much boxiness in the sound, without increasing any of the dips. Don't worry about these dips anyways, most of them is inaudible. So this is how you do the rest of the speakers. Now it's EQ-CH, the next one is EQ-FHL. Again, go and check its distance, apply tight right window according to the distance of the speaker in milliseconds, and then apply psychoacoustic smoothing, and by using the same target SPL and same settings for EQ, no boost, match response to target, and generate only the filters, not the predicted response. I can show you the last filters we created. This one and this one, as you see, are from 500 Hz to 20,000 Hz. For practicality, actually, you can make an Excel file like this and fill up these distances from your Odyssey measurement for every speaker. Here 201 meter, 174, 195, etc. And determine the speed of sound for your receiver. Let's say 300 meters per second. Look, if your front left speaker is 2.01 times 3.3, 300. In fact, more like 2.30 meters to the listening position, central listening position, okay? And Odyssey is calculating 2, then your receiver speed of sound is 300 meters per second. If it is closer to 229, then your speaker is correctly applying 343, okay? This is all you need to do. And majority of receivers are still at 300, so let's keep it at 300. And here you calculate the speaker is 2.01 meters to the listening position, divided by speed of sound, F4, times 1000 to convert seconds into milliseconds, so 6.7 milliseconds. And double click. You can now much faster change the IR window sizes here. EQ, FHR, we were here. Okay. And target, as always. We applied window to this one, I guess. No, not yet. How about this one? Yes. Okay, EQ FHL. Here FHL 8.5. Obviously, these are not very accurate distance settings. Odyssey has deviations, especially for the subwoofer usually. These are good enough, but if you are obsessive compulsive, you can always, after setting your distances accurately, come back and redo the last filters. But it's not gonna make an audible difference, I'm telling you. So once you apply this right window size, and FHL has become like that. No, it hasn't, because this is 21. We have to deal with 47. This EQ FHL. Yeah. Okay. Now it's shrunk, and apply psychoacoustic smoothing. And these settings do not change from measurement to measurement, and generate measurement from filters. EQ FHR. Window is from here 8.5. EQ, psychoacoustic smoothing. There are keyboard shortcuts for these things, by the way. Try to remember them, because this really takes a lot of time. Measurement from filters, and then EQ FL. First IR window, FL 6.7 milliseconds, 6.7. EQ, psychoacoustic smoothing, match response to target, generate measurement from filters, and the next one. Okay, finally all filters are generated from the psychoacoustic smoothed high frequency responses. Now the final operation is all trace arithmetic. Now, for example, for the front left speaker, we have those three filters. Let me find them. Filters FL, filters EQ FL, and filters EQ FL. One more time, it must be here somewhere. Here. We have these three filters for front left speaker, okay? Now, the filter that we need is a combined one, which is a combination of 24, the first one, and then anything with filter and FL in it. Filter EQ FL is going to be, which is 50 multiplied, okay? And as you see, it combined these two filters, and with the multiplication, which is going to be at the end. That was a very good screen shift there to confuse things even further. And we were at 50, so it's going to be after 50 another filter with FL, so 70 filters EQ FL. Again, A times B, generate. So now we have just one filter, which is a combination of all three filters, which we're going to call FL. Okay. To do this faster, a good way is to start from the first one, which is filter C, and then you multiply it with filters EQC and generate, and then 1844 generate, and then 2046 generate, like so. We do the FL one more time here. Where was I? Okay, it doesn't write the numbers. Filters FR, EQ FR, filters RHL, EQ RHL, filters RHR, EQ RHR, filters SBL, EQ SBL. So Auro 3D is really a bit of a hassle to correct. There are too many speakers. SLA, SLA, SRA, SRA. You have to check here that you're always multiplying the first two filters. If you see anything going on here, then it means you kind of messed up here. Okay, finished. We are at subwoofer. Subwoofer is a different story. Now you go to the first A times B, like this one, and you have to find the first A times B here. Let's get rid of FL. I was just showing it to you. It makes the order confusing. So we started from C. The first A times B is gonna be filters EQC, the last one, this one. So now we do this. 78 times 66. And then 79 times 67. Just go one by one. 80 times 68. 81, 69, 82, 70, 83, 71, 84, 72, 85, 73, 86, 74, generate, 87, 75, generate, 88, 76, generate, 89, 77, generate. I think 77 we are finished. Yeah, because 78 is another 8 times B. Now we can write their names starting with A times B calculation. So this is C, this is CH. I see it here, okay. This is FH out. SI. Let's select and see the filters if they look good and everything seems logical. All the filters selected. The subwoofer filter where it was here at the very beginning, which is this one. These are our filters. Now all we have to do, unselect subwoofer and any other, only the filters are selected. Go to export as text, use custom range 10, 22,000, custom resolution 48, this is more than enough, around 500 custom curve points. That's like 500 band equalizer that we are applying here, just so you know. And comma separated, it has to be, and do not include any comments or headers. Must be ticked because of my HTML skills, otherwise it's not gonna understand. And it's already 3 columns which has phase information, and the snippets managed to remove the last column before pasting it to the ADY file. Otherwise you would have to take a magnitude copy of each and every filter, which is another set of work. So it will ask you to select a folder. Let's select main tutorial folder, make a new folder, filters, select this folder, voila. And now in tutorial, in filters, as you see, we have all the filters saved from 10 Hz to 22,000 Hz. And lastly here you have to save the subwoofer filter. You can do it on its own. Where is filters SV1? Here, file, export measurement as text, and this time from 10 to 250. Again 48 is fine, everything else the same. Okay, ignore this message and name this SW1. It's important that the names of the filters, the last filters, are the channel names. Otherwise the snippet will not work. It's not a big deal. You have to know your channel names anyway. These are weird Aura names, but other Atmos channel names are pretty straightforward. So export this one. So I'm repeating because for some reason it saved it somewhere else. 10 to 250, 48, PPO, SPL, comma, do not include. Okay. Yeah, this is the problem. It is not under tutorial, it should be here, and save. Now under this filters folder I have 1, 2, 3, 4, 13. There is one missing. Wasn't this 14 channels? Yeah. What is missing? FL. C is there. CH is there. Interesting. TS. Yes, TS is missing. Okay, what happened to TS? Let's see. We didn't make any filters for the poor TS. Yeah, because I always stopped at a subwoofer thinking it was the last measurement. Not even the first set of filters for TS, I guess. No, poor TS. Okay, TS will have to go to 115.6. So this is gonna be a wrap up of the full coolization process. 551. TS EQ, it should start from 20 to 200. 551 this target, and then match response to target. Okay, generate measurement from filters and predicted. So this is the predicted, only corrected until 200 Hertz. Then you go to the after correction response and make it from 200 to 500 this time, but with no boost. And match response to target. Generate filters, generate predicted, and go to predicted. IR windows, check from your Excel file. TS timing 4.6 milliseconds. This is a top speaker, so it's very close to the listening point. 4.6, and after 4.6 is applied to EQ TS, we go and apply psychoacoustic smoothing, and from 500 to 20,000 this time. Again 0 0 no boost, match response to target. As you see, the TS is very well tamed. This time only generate measurement from filters, no need for predicted. And finally, as you see, these are our TS filters, all three of them. The first two should be multiplied first. And then with the multiplication, we multiply the last filter and come up with this. And this one we have to call TS because filter names should be channel names, otherwise the program is gonna have trouble matching them in the ADY file. Finally, you have to save that in the same folder. Export measurement as text. 10 to 22,000 was it? 48 and comma, and don't include headers, and save under filters here with the name TS. When you use export file and export them all at once, it automatically names them according to the measurement name. So if you keep the names here in order, it is good enough. Okay, now we have 14 filters, not measurements. Now you go to my second HTML code named correctn. Double click. First, choose the ADY file, the perfect speaker version that we created at the beginning of the tutorial, okay? So that there is gonna be no Odyssey correction. It's ready. Then process ADY and select folder to upload filters. Click that. It shows you which channels it wants to load filters for. Double check here, everything is correct. Okay. Filters are here. You go there, then you select every filter. If there are more than one C correction, for example, you select the one that you want to use as correction. So select them all and click open. That's all. Now filters applied ADY is already produced and you can just save it. Takes a little while, but when you see it here, it is saved. Now let's check. Filters applied. So this was the original measurement. As you see, it has no custom target curves, but in our one, the responses are perfect. So no correction by Odyssey. The only correction is what we applied here at 536 custom curve edit points for each and every speaker correctly placed. Because subwoofer range is only to 250, subwoofer has only 225 items. So custom target curve points are added to the perfect speaker. Distances are still what Odyssey found. You can change distance settings here in channel report. Okay. Now, just before we move on to speaker distance alignment, a couple of things to remind. These are the original responses and these are our filters. And I also tick the target. Now anything else we can delete. We are already at 108 responses here. So toggle selections and remove the selected measurements. And now select all. Now we are down to 28. In Rev preferences, here, for example, speed of sound is 300 for me. You have to change it here when you're calculating speaker distances. If it's 343, take it 343. Maximum measurements, the limit is 199 and I use it at the limit. As you see, you can easily go above 100. Other than that, generic equalizer settings, analysis, we don't do any measurements, we don't do any calibration, nothing. Only a couple of preferences here you have to deal with for using Rev. Another thing, in this particular case, the subwoofer was right on target, okay? But in general, it will usually be a little bit off compared to other speakers. Subwoofer is normally a little bit off the target, something like that, for example. And before you equalize it, you have to adjust its volume and apply a similar volume setting. For example, I could do this and then equalize it and get rid of all these, but usually you have to leave some dips. This subwoofer ideally is best here from what you see. It also depends on where you're gonna cross over your speaker. So make sure you adjust the volume of subwoofer here in multiples of 0.5 as best as you can to the target curve, and then equalize and apply the same level setting also in the receiver or in the Odyssey file, which is here. Custom level for subwoofer is null, for example, x minus 2.5 here, okay, or plus, or you can change it in the receiver at the end. Similarly, the distances, they are under channel report and you can enter them. If you enter all of them here, then you will have a proper ADY file, which whenever you transfer to receiver will reset all settings to ideal. Otherwise you have to save it in the receiver. I mean, there are many options, but this is how you change them. And with this calibration technique, which is optimized, you should keep dynamic EQ and dynamic volume off. Otherwise you will never be on this ideal Harman target curve. 148 smoothing is optimized, meaning I tried every other smoothing. 5 dB boost is optimized, 200 Hz is optimized, 500 Hz is optimized. They have been tried vigorously for every possible frequency range. And for Multi-EQ X users out there, I just deleted them, but I think I can get them back. Let's wait for 108 measurements to open up. 75, 80, 85, 90, 99, 108, yes. For example, for TS, the first set of filters, you can see here their peaking filter values. Frequency 1433. This is gain minus 5.2, and this is the Q value. You have all the filters here. They belong to different bands. This is between 200 and 500. Frequency, gain, and Q. And the first one is between 0 and 200. Frequency, gain, and Q. So you can manually enter all these filters to Multi-EQ X and basically apply the same correction. You will need to export Odyssey measurements to REW to be able to apply cross correlation align and vector averaging. Then you will get similar results from Multi-EQ X as well. Now let's go back to distance measuring. First, let's calculate the final responses, because those filters change impulse peaks timing a little bit, especially heavy equalization on the subwoofer can make a difference. So it's best to align speaker distances after equalization. Okay. Normally you should remeasure every speaker after equalization with Odyssey and the filters on in the receiver, but for Mac users and for Aura this is not possible, but this is gonna give very similar results. These are all the original measurements and these are all the final filters. Toggle and remove and select all, just to see what we missed. Doesn't seem we missed anything. Okay, now we are calculating the proper responses, but to calculate responses properly you have to remove all smoothing. No smoothing to everything. And now trace arithmetic, and let's start. 1 times C basically. CH times CH. FHL times FHL. Surround back right, surround back right is not here. Nice. Okay, looks like I deleted surround back right by mistake. What I can do is open original one in another REW session. And save measurement. And close this extra session. Go back to my original session and drop that measurement on here for surround back right. This was a filter, not a measurement, hopefully. Yes. So where were we? Trace arithmetic, surround back right, and SLA, SRA, and top speaker times top speaker. We can move surround back right to where it belongs. C1. CH1, meaning this is after correction. FHL. TS. Okay, now these are our final measurements after correction, speaker responses. They had all. Okay. And after 1/48 smoothing, as you see, we have a pretty flat response. And this was the ideal target. Now, copy selections to overlay graphs, and from now on, we are in mount overlays. Plot normalize, show points when zoomed in, ticked, so you see these dots. Now, where is our Excel file? You have to accept one of the Odyssey measurements as correct, and they are not usually very wrong, but it's easy to measure front left or front right or center speaker to the LP, central LP. So let's think of that as correct. When I say correct, if your speed of sound is 300 and your real distance is 2.3 meters, then you can think of FL at 2.01 as correct. Okay. Now, when FL is correct, clear selections, choose FL1. You're trying to find the correct distance of C1. Okay. To be as accurate as possible, keep them both on the screen. This is the limit, and keep them as pointed as possible, so that you can take everything at one measurement. This is the front left speaker. This is the center speaker. Center speaker is arriving earlier than the front left speaker, which means its distance should be decreased so that the receiver sends it with a little bit more delay. Okay, it will think it is closer, it's gonna delay it a little more. It will come as late as the front left speaker. So when it is to the left, you have to decrease the distance of it. To the tip of the front left speaker, if you have to be very accurate, you do this with right mouse click, by the way, also pressing simultaneously keyboard control key. Also, I have to remind you that we are at 300 meters per second speed of sound. Okay, everything we see on this calculation is correct, and we can readily key it in the receiver. 22.1 centimeters or 0.22 meters. Okay. So FL was 2.01, and let's add here difference. This was to the left of the front left speaker, so this was minus 0.2221. Actually, it is 22. Okay? Let's do like that. Result. Distance. So this should be this F4, always from FL, plus this one. And accurate to 2 digits after the decimal. You can copy this formula all the way down. So 1.79 is the actual distance of the center speaker. What did Odyssey find for center? We don't need this anymore. FL 2.01, we left it that way. Channel report 174. So we have to make it 179. Only 5 centimeters error with Odyssey. This will be very accurate. The impulse peaks will be all on top of each other at the end of this. Now FR. Okay, FL1 is our reference speaker. We accepted that it is distance in Odyssey is correct at 2.01. And if it's in fact 2.00, it really doesn't matter. It just changed the Atmos bubble size by 1 centimeter. But everything will be still relatively perfectly timed. So I mean, be accurate here because the receivers are not accurate to less than 3 centimeters, so do your best at this stage. FR1 to FL1. Again, FR1 arrives earlier than the front left speaker, so it's a minus from the tip of this one to the tip of this one is 0.024 meters. They are almost on top of each other. Minus 0.024, sorry. So 199 is what FR should be. We go to our file and find FR, and channel report should be 199 instead of 195. 4 centimeter difference here. Now RHL1. Where is it? Bottom of the graph. Okay, RHL1. RHL1 compared to FL1 is arriving later than FL1. It's on the right of the front left speaker. So its distance should be increased compared to front left by 0.03 meters. XL plus 0.03 this time, and 2.04. Sorry, this wasn't SRA, this was RHL. So here 0.03. So 2.04. Where is RHL? I have a feeling it's here. I have a feeling it's here. Yes. Channel report. So 2.04. So Odyssey is not doing such a bad work, as you see. Only 3 centimeters difference here. This is how you correct the distances of all your speakers. Once these distances are set, all the impulse peaks will be gathered. Now the most important part is the subwoofer. And let's create the corrected subwoofer response after the filters. So SW1 times the filter SW1. And this is our corrected subwoofer response. Call this subwoofer 1, 1. Okay. Now in overlays, we have the FL speaker, which we picked to be reference, and our subwoofer and fit to data. Here is the subwoofer response. You can't really adjust it to the impulse peak because, as you see, you have to increase the subwoofer by 12.61 meters over 2.01 of FL's distance, so it should be 14.61, which you cannot do and which you don't need to do. What you need to do instead, this guy, by the way, is using mini DSP. It's obvious from these distances, but still, Now, the speaker responses is like one down, and then the peak is the second up, the second peak, which reverses direction. So let's see when the subwoofer is doing it on a very large scale. Goes down and then goes up. So this peak here, okay, is a very nice impulse peak to equalize with the rest of the speakers, which, to be accurate, still cannot, yeah, only now, and open them up as far as possible. Now they are both on the screen. So which is the highest peak of this one? Well, the peak is in fact here, okay, but this looks like more, doesn't really matter with the subwoofer that much, but yeah, could be this one. So from this peak here, which is slightly higher than the rest, measure all the way to the peak of the front left, as accurate as you can, and 3.577. Go to your Excel, and it is on the right. It is later than the speakers, so it's a plus 3.577. So subwoofer distance you need to enter is 5.59. Very accurately. Here you go to channel report, and instead of 369 you enter 5.59. A 1.5 meters difference. And that's it. You don't need to do anything else. When you send this ADY file to your, save it and send it to your, okay, this is a weird message, leave me alone. When you save to disk and name this one, distance is corrected, and save it. And then all you have to do is send it to your phone, and from the phone to the receiver, and you're all done. I hope you enjoyed this tutorial, and finally Mac users and Aura users can accurately calibrate their surround system. Thanks for watching. Don't forget to subscribe. Goodbye and good luck.